APL. And what I'd like to do is briefly expand on my background, my involvement with APL and other languages. Won't take long about that. And then start talking about what it is that I've been having fun with working in APL for the last few weeks. Show you a horror slide of what I was doing before I started doing this work in APL and the APL that it reduces to. And then if we have time, give you a quick demo of the genetic algorithm stuff that I've been doing. None of this is on the memory sticks you've got, I'm afraid, because I'd originally planned to give this presentation using a whiteboard and flip charts. When I saw the size of this room, I realized it wouldn't work. So this is quite a recent presentation. That's why I ducked out of most of yesterday. But the content will be, I hope, appearing in the next issue of Vector. So you should be able to get extra detail from there. I've been in IT for quite a while. I saw my first computer in 1958 and wrote my first program in 1958. And I've been writing software pretty well constantly from then on. I was quite young then, by the way. And initially, the languages that I used were relatively low-level languages. And in 1968, I had what was the first experience of APL. I was at that stage a student working in a summer vacation for IBM in their education center in the UK. And one of my fellow instructors told me that there was this wonderful new language which he was experimenting with, which looked like it was going to be pretty good for computer-assisted instruction. And I went along and I saw these fantastic, beautiful symbols. And the only trouble was that at that stage, APL was available on that machine and that machine only for 1 hour a week. So it wasn't really a viable choice for me to play with. But a few years later, I saw it again and remembered how much I'd been interested before and tackled a real-world problem I had and just fell in love with the language. And for, I guess, the next 14, 15 years, I earned my living full-time, either writing APL or working with other people who wrote it. And at one stage, we had about 40 of us doing nothing but APL. But sadly, a lot of our work was in the mainframe market, and that declined quite rapidly. And from about 1987 onwards, we really needed to find other ways of earning a living. And I came across Smalltalk. Didn't love it quite as much as APL, but it was pretty cool. And in particular, if what you were trying to do was build GUI applications in those days. And we were beginning to see graphic user interface operating systems coming out a little bit later, but certainly by 1990, a lot of people were trying to build applications that used GUIs. And you had a choice of using something like Smalltalk, which was relatively straightforward, or creating about 20 or 30 pages of C and spending most of your time trying to find out why you'd crashed with a null pointer. Smalltalk lasted for a while, but that market too declined. And in 1995, I came across Java. And compared with APL and Smalltalk, it was a pain. But I've told this joke to someone already. Somebody said the other day, so why do you do Java if it's so unpleasant? Anyone here heard of a guy called Willie Sutton? He was quite a famous bank robber. In fact, at one stage, he was on the FBI 10 most wanted list. And the story goes that some journalist asked him, "Tell me, Mr. Sutton, why do you rob banks?" And he said, "Because that's where they keep the money." So that's, I'm afraid, what I did Java for quite a while, and still do from time to time. But as of last year, I decided that I really, really wanted to get back to playing with some ideas which were the basis of a master's thesis I did back in 1974, And I've never really had quite enough time to move those ideas forward, but it's a research area which, it happens, nobody else has really done much in. So it's still fresh and available. And so I started recreating my master's thesis program, which had been written in Algol 60, recreating it in Java. And as you'll see towards the end of the presentation, that turned out to be more of a struggle than I really felt I could put up with. And so I switched to Python, which is a language I've used quite a lot. It's a scripting language. It's interactive. It actually has some quite decent array handling in it. But still, I found myself just having to put in too much effort for the reward I was getting. And having had periodic meetings with Gita and Morten, thought, I'm going to give a shot at doing this in APL. And suddenly, everything started coming out very quickly and working really well. The research that I was doing is actually research into neural networks. And maybe if I get asked back next year, I can tell you a bit about some of that if people are interested. But in order to do that, as a sub-problem, I had, in effect, to try and find better ways of wiring up the simulated brains that I was creating. And I wasn't smart enough to do that. So I decided I'd use evolution instead, because that's worked pretty well so far, and got into the area of genetic algorithms, which I have been using to try and wire these things up in better ways, but they have a lot of other applications as well. One thing I'd like to check before we get into the main material, how many people here have used genetic algorithms in work they've done? So it's okay if you want to leave now, because this is going to be real basic stuff. And if I get anything wrong, then give me a shout. But they're very interesting, and what I thought I'd do today is spend probably about 15 minutes taking a high-level view of genetic algorithms and how they're supposed to work, and then have a very quick look at the APL implementation. APL turns out to be a really excellent vehicle for implementing these things and experimenting with them. And all of the code that I'm using here will be in the vector article, so if anyone wants a copy of it, also just let me know and I can email it. So there are an awful lot of optimization problems in the world, and quite a lot of them are optimization problems where you can't easily find an analytic solution, an exact solution. The best you can do is some kind of series of approximate solutions which can gradually get better. And a couple of real-world examples. If those look a bit fuzzy to you, by the way, it's probably because you spent too long in the bar yesterday. They're certainly looking fuzzy to me. So I'll try and talk you through them, though. Over on the left, the colored stuff is kind of an iconic representation of a real-world problem in which a company might have several suppliers, those are the yellow S boxes, who provide the things which this company, this fictitious company, sells to its customers. The suppliers are scattered around the country. There are a couple, maybe more than a couple of warehouses in different locations in the country. The customers are geographically dispersed as well. And one of the things you might be worried about is minimizing the cost of getting stuff to the warehouses and then getting it off to the customers. And you can clearly describe a possible solution in terms of the number of products that you stock for each product in each warehouse. So you can represent a particular solution just as a vector of whole numbers. And you can also, if you know what the transportation costs and the holding costs are, you can clearly work out for any given solution how good, how expensive it is. Completely different problem domain occurs if you're in the aircraft manufacturing business. And if you're designing aircraft, one of the things that you need to look at is the shape of the wings of the aircraft. And you may be able to reduce that to a fairly small, for a given type of design, a fairly small range of numeric parameters, no longer integers, they'll typically be real values. But once you know those four values, you know the shape of the wing of the aircraft, and you can work out whatever it is that you want to optimize, perhaps the ratio of lift to drag, I don't know. So if you've got problems like this, where you have lots of possible solutions, and you can describe each solution by a vector, then genetic algorithms are one way to try to find good or progressively better solutions to that style of problem. And effectively, what you do is you treat each of those vectors, those numeric vectors, as if they were the chromosome of a living organism. And you work out how good the solution is, and that tells you something about how likely it is that that organism will pass on its genetic material to the children that come after it. So, key ingredients. The genetic algorithm is going to work on a population of solutions, and it's quite possible, in fact, that you may have several identical solutions in that population. These are not necessarily unique. You describe them as a vector, you calculate the value. The thing you have to have is some sort of function which will take a vector of numbers and turn that into a value, a measure of goodness. And the assumption I'm going to make in what follows, by the way, is that number is positive, that the value may vary in various ways, but it's going to be a positive number. And what genetic algorithms try to do is to imitate the way that nature takes populations of organizations and helps them to adapt to the environment they exist in. And typically, genetic algorithms will use 3 techniques to help them do that. I'll run through each of them, and they're fairly easy to understand. The first, and one of the most powerful, is the idea simply of selection. We'll look at that in a second. And there's something which is a little bit more complex called recombination. And the third thing is mutation, in probably just the sense you imagine it. You actually may want to damage the genetic material in order to try experiments, if you like, with solutions which otherwise you wouldn't have considered. And when I first started doing this stuff, I was under the impression that mutation was really the key to it all. In fact, it's not. Mostly selection does the job, and recombination helps a bit. And mutation is really just there to avoid us getting trapped in areas in which we found a fairly good solution, but it's by no means the best. One of the things that mutation may be able to do is to take us off into other areas that we wouldn't otherwise examine. So let's look at each of those. First of all, selection. Each time you do a selection on a population, what you're trying to do is find the good guys, that's the green box there, and the not so good guys and the really not very good at all guys, and make sure that you have more of the good ones in the next generation and fewer of the bad. Pretty much as simple as that. There is one question that probably going through your mind. Why don't you just pick the best of those and run with it? And of course the answer is it may be the best of those, but it may not be the best solution. And there's another reason why in some situations just going for the best solution you found and focusing entirely on that is not a good idea. In the real world, the trouble is the environment changes. And as the environment changes, the fitness of each element of the population will change. And you may discover that you need now something in the population which was there and you've got rid of it, and that would be a real problem. So actually maintaining diversity in real life and in some sorts of artificial problems as well. Maintaining diversity is a safety measure that's a pretty important one. But in the version of selection that we'll be looking at, as I said, I'm going to assume that fitness, my measure of fitness always gives me a non-negative number. And that means that for my population, I can normalize my sets of fitness. And if I do that, I'm going to have a set of numbers between 0 and 1, and they'll all add up to 1. So I can treat those as probabilities. And the simplest and most effective way of picking who gets to have children is to look at those probabilities and pick from the population using those probabilities to constrain my choice. And as I said, selection actually works pretty well, but there are a couple of reasons why it may not be enough. One of them is that the population is finite, and it's highly likely, if you have a large solution space, that your finite population does not include anything that is optimal. It may not even include much that's good. In which case, you can select and select and select. It's never going to get better than the best in that population, and that may not be anything like good enough. So the first extra trick we try is something called recombination. And here, I've gone right into the genetic representation of a couple of solutions, my vector of numbers. In this particular case, and in most of what I'm going to be doing, I'm looking at the case where my solution space is finite and each of the numbers is a whole number. You can do something similar with continuous variables and an infinite space, but it's easier to understand what's going on in the finite integer case. So parent 1 is characterized by the vector 375829137. I have no idea what that means, and I don't care, so long as I can work out the fitness, which I'll need for selection purposes. Parent number 2 has a completely different vector, and with recombination, what one does is imitate a process that happens for real when cells are reproducing, in which I start off taking the individual, these things effectively are genes. And I start off taking the genes from parent 1, and then something goes wrong with the process. And as a result, for a while, I start copying the genes from parent 2, and then something might go wrong again. And I switch back to picking the genes from parent 1. So going wrong in the sense that the machine that's doing the copying really needs to produce accurate copies. And yet, it does this thing which makes for inaccurate copies from the point of view of one parent. But you're right, it's a good thing it does that. The process though, is actually, from one point of view, the process breaks down at this stage and produces that effect. But let's agree, it's a good thing that it happens. It's a good thing because it means we can come up with solutions which didn't previously exist. So that the child of those two, under recombination, if the recombination the crossover happened to take place at those 2 points, is going to be something which has inherited some characteristics from one parent and some from the other. I can almost see the eyes of the APLers thinking in terms of how you would represent this in APL, and it's pretty straightforward. Third thing, mutation, even simpler. You take the parent, you try and make an exact copy, except that in one or more places in the copied genetic material, the copied vector, you make what is essentially a random change. Simply pick a possible value at random. So that's the theory, pretty straightforward. This is actually not part of the GA material. It's something I was working on. This was my moment of truth. And what I'd been doing was, in my neural network stuff, trying to get a decent, fast, simple way of presenting the state of a matrix of neurons. And I just wanted to see how fast are they firing. And I had a lot of numbers, and I wanted to very quickly see what the whole thing was like. And this is part of the Java that did that stuff. It's not all of it. There's yet more. There are other methods around involved. What it's doing is that, which is scarcely an intellectual challenge. And yet I had to do all that typing, and I thought, hey, I do remember there was a better way of doing this. So what I'd like to do, I'm actually massively underrunning, I think, but that's okay. What I'd like to do now is, I think I better sit down for this, very quickly give you a run-through, a demo of the application. And I knew I'd be late in the bar last night, so this is a canned demo. But we can take a look at and talk through some of the code, because nothing here is complicated. You'll see a little later just how little code there is and how straightforward. Because I'm playing around with random numbers, the first thing I'm going to do is try and make sure this is a repeatable demo. So I'm going to set a nice safe value for the random link. And I'm going to create a population. I should warn you that in order to make it easy to see what's going on when we run this stuff, I've taken a totally unrealistically simple problem to which anyone in the room can immediately work out the optimal solution. But what I'm doing is building a population of possible solutions to my problem, which I'll tell you in a second. And that problem is defined in terms of just three numbers. A vector of three numbers characterizes an individual. And in the first position on that very short 3-gene chromosome, there are only 2 possible values for the first gene, and there are 3 possible values for the second gene, and there are 5 possible values for the third gene. And the really difficult function which I'm trying to optimize is the value is the sum of the numbers. Okay, so we can work out pretty quickly. Anyone here have trouble working out what the best solution is? It's going to be, in case you were in the bar as long as I was, it's going to be 2, 3, 5. But of course the population is going to have, well, not all possible solutions. I've said that I want to have just 10 individuals in my population with quite a low mutation rate. I want there to be about 1 chance in 1,000 that any particular gene gets changed, but a fairly high recombination rate. If you think of a matrix, which will come easy to us all, if you think of a matrix in which the rows are members of the population and the columns correspond to positions in my vector, what I'm saying is that 0.3 out of all of those positions might be a crossover position. So if I have a population of 10 with 3 positions in each vector, I'm going to have round about 9 or 10 crossovers taking place in total every time I reproduce the population. Let's create that, and then population that I created there is actually an object, an instance of a population class, and I can look at the individuals that make that population up. That's just a matrix of numbers which represent what role has given me as the values for the genes. And we can take a look at that, and you can tell already that none of those is the optimal solution. We've got exactly the problem that I described to you earlier. I haven't got a single 2, 3, 5 anywhere in that set. So none of these are ideal solutions. And if I just used selection, therefore, I would never hit the optimum. There's my fitness function. I already told you what that was. If I take a look at that whole population and calculate their average fitness, it's 5.9. Which is way off the optimal value, which is, just see if you're awake, 10. Good. I could see someone typing plus reduction 235. That's excellent. And if I then select from that population, select is actually a user-defined operator which takes the fitness function as its argument. And so I'm going to select using that fitness function, and what I get back is slightly better. It's only slightly better because all I've been able to do is pick more of the good ones and fewer of the bad ones, just like we saw in the diagram. So selection on its own, while it will help, is not good enough. What I would like to do, let's actually... I'm going to run something called generate, and generate is going to take a fitness and a number of generations I want and breed my population for that number of generations. And what this whole thing, therefore, is doing is running 10,000 generations on that quite small population, and then at the end it's going to take a look at the individuals and see what their average fitness is. And what I'm hoping for is quite a high number. Not 10. I would be worried, actually, if I got a 10 there, because that would imply that I only had the optimal solutions left. And there are some situations where that might be a bad thing. That was, you could see a pause then, but it's doing quite a lot of work in 10,000 iterations. And I've played with a few other tools. The impression I've got is that without having thought much about performance, the APL implementation runs at a speed that's really quite good compared with most commercial products, which is, I guess, no surprise to us all. None of these things, let's actually open the, I'm still delighted and surprised by the existence of the Workspace Explorer. So forgive me, remember I've been away for a while, so these basic things. There really aren't, look at the right namespace, Romilly. There really aren't that many parts of the, you can't see it. This is a conversation I had with the guys in Dyalog not long ago. Workspace Explorer is great for looking at individual things, but what I want to do, actually, is just show you everything. And it won't take long to take it in, so... So pretty well everything is a one-line defin. One or two of them are there just in order to make exposition and experimentation easier. Breed is about the hardest, and the reason that's so long is because I haven't been able to kick my Java habit of trying to give long, meaningful names to things. And I'm beginning to realize that in APL, that's probably not such a smart idea because the name is probably longer than the implementation. And I sneaked in a couple of very dumb objects there, which I haven't listed because they really are just data holders. Can I drop the font size a little? Can you still read that? Okay, so that's the whole thing. I'm going to hide the run function actually because it's really embarrassing. That's the entire genetic algorithm stuff. And breeding basically says I'm going to select and then mutate and then recombine. Mutation is, as you'd expect, pretty straightforward. You're simply generating some random values which you use to pick from the permissible range of chromosomes at each place in the genes in a particular chromosome. The only thing which is, can I use one of the whiteboards, one of the flip charts? I think I can most easily. Everyone see that okay? I can most easily do this as a diagram. This is your homework, okay? Because this is a problem to which I have a solution, but I'm sure there is a better, shorter solution. And the problem is, remember we said earlier that if you had a set of fitness values, you could normalize them, and then you had some probabilities, and I represented those probabilities as values around a pie chart. So let's say that looks like it's about 42%, 0.42, it's probably about the same, 0.3, 0.1. Except, of course, in a population that's large, I'm going to have lots and lots of those values. And these are numbered by some arbitrary numbering which identifies the individual. What I want to be able to do, given that there are lots of these values, lots of these individuals, is I want an efficient way of using those probabilities to select the right number of copies to make up my population. And also there is a trivial solution that does an outer product. The trouble is it does an outer product, and that's an outer product in the size of the population, and therefore it's order n squared, and therefore you have a large population. It begins to run a little slowly, and you're doing this over and over and over and over again. So my soul rebels against that, even though it's conceptually simple. What I'm looking for is something that's simple and fast when there are lots of things in the population. Okay, thank you. Good. Great. I'll take a look at that. Oh, it's okay for me to copy the homework. I'm the instructor. That's great. Any questions? Roger.
I'm encouraged that you have logical scan.
Yes. I was delighted, and then I suddenly realized that, of course, I'm doing it in the easy direction anyway, so I don't get the full benefit of your work. But not equal scan is the natural way of expressing that recombination. It's you see it immediately comes to mind. It has to be the right way to do it.
I think that's what actually happens in this.
Yes.
Yeah.
I wouldn't be surprised. The other thing which I'm not sure whether I'm encouraged or discouraged by this is that there's almost no second generation APL there. And at first I thought that's because, I'm too old to. I still regard nested arrays as a slightly dangerous innovation. But actually, I think because this is essentially working with a matrix of values and trying to work out fitnesses and stuff, the natural representation, the obvious representation, is very, very easily expressed in old-style APL. Anything else? Hi.
In your example, all values were visible.
Yes.
So how would you start saying some solution?
There are really only two approaches to that I'm aware of, and they're both bad. At least they both have undesirable characteristics. One of them is just that you slug the fitness function so that anything that's impermissible has a fitness of 0, in which case it won't survive. But of course that makes for potentially an awful lot of wasted computation if the percentage that are feasible is low. And the other thing is something which may or may not be possible, and if it's possible, may or may not be easy, and usually it's possible but hard. And that is to make sure that you use an encoding of the values which can only generate legal values. And so in my neural network stuff, for instance, the biggest challenge was to find a good encoding which was guaranteed to produce a workable, wired-up bit of brain. Once you've done that, then this works very well, but that's the hard bit. And in my experience, that's generally the case. So if you're using this, for instance, I think Adrian did some work on portfolio stuff.
And zero is a number you never use. So what we did was, if you broke the law, you still didn't set the fit function zero on the wrong side of that. Because if you did that, you found you had no legal solution in the argument itself. Because the chances are, the whole thing is invalid in itself. So you have, fitness is composed of two things. If you think of a person or breaking the fitness. If your arm gets fitter, let's say by having it on the neck, so you need to leave. But it also has to work perfectly. And so essentially what you have is the fitness function cuts from two sides. You have things that add to the ability of the solution to grade, and you also have things that enable it to work perfectly. And a typical fitness function is Mutation, which will, for a fairly important constraint like breaking the law, it will look quite like a step, but it's not a step. It's a logistic that never actually goes to zero, never actually goes to one, and never quite goes to zero. So even if you're pretty illegal, you're more fit if you're only pretty illegal, and you're more fit if you're very little illegal.
Going back to your bond,
Even though the numbers are tiny.
going back to your bond example, to me it would be intuitive that buying a bond and selling the exact same bond should not be allowed. You should make a decision to buy it or sell it, but you shouldn't be able to both buy it and sell it in the same portfolio. You could be zeroing it out or doing just net buying to something. You wouldn't make that, you would still use a logistic function on that to try and weight it rather than.
And I wouldn't. I think what I would try to do, and I haven't solved that problem. I think I'd look for an encoding that ensured that didn't happen. And sometimes when you do that, understanding the encoding suddenly tells you, hey, there is an analytic solution to this, or something close to it, and I can actually take a much simpler combinatorial approach.
A lot of people with real-world GA problems, you can kickstart the program by your initial population can be designed to be not awful, and then you evolve from that, and you try and get some rules built in. Yeah, you build it, and the real world gets made. But the basic algorithm is that you try and preserve the, you must keep your white rabbit as long as you possibly can, because they may want it.
The neural network research which led me to do this is I'm expecting to apply it to real-world problems, but at the moment that's probably 3-4 years away. I'll give you a bit of background. There's a guy called David Marr who in the 70s started producing, or actually the late 60s, early 70s, started producing models for 3 quite interesting parts of the brain. And what I did for my original thesis was to simulate one of them. And in itself, it's quite a useful component that could be very widely applied in a lot of situations. What he thought the cerebellum did, and what the simulation turns out to do pretty well, is it's a kind of content addressable memory in which it remembers the context in which something happens, and the next time the context comes up, it knows to do that again. And it does it in a way that is very mean with hardware. It's very efficient in its hardware use. And the other 2 were different sorts of memory. And I'm pretty much convinced that with those 3 things at one's disposal, you can build a system which you can teach to understand natural language. Okay, and that then does begin to have some interesting practical applications. But that's if I do anything in less than 3 years, I'll be amazed, and I'll probably not be able to make real progress at all, because we know this is a very hard problem. But well, in this particular example, and this is true actually for most of the people who have tried to apply this to building neural networks, you usually start out making some quite restrictive assumptions about what's possible. And of course, real evolution doesn't do that. But it's got a very much longer time scale to operate on than we do. What you can do, though, is the key to getting close to what you're hoping for is to use the genes to encode an algorithm which, when executed, can structure things. And if the little language which you're encoding is sufficiently rich to be Turing complete, then it's going to be able to build anything. And there has been quite a lot of experimental work in that area with varying degrees of success. But my starting assumption is I don't really need to do any dramatic mutation, because if this really is the way that these bits of the brain work, we already know they work pretty well. And it's just the wiring, the detailed wiring, that one needs to try and tune. And so I've got, from that point of view, a fairly simple problem to solve. The cerebellar cortex bit has very well-defined performance goals. What you're trying to do is make sure that when you provide a lot of contexts and the training cues, that when you show those contexts again, you get the right response a very high proportion of the time. Well, in fact, in order for things to work well, you have to do lots of training. So I've actually got a big population of networks, and each network will then go through many lives in which it's subjected to a series of stimuli, and I take a look at all of the sets of performance values. And what I'm aiming for is something that is pretty good at remembering and doesn't go wrong and doesn't get stuff wrong very often. And it's fairly easy to quantify that. So now I've got my fitness function. And of course, it does satisfy the applicability criterion that there is absolutely no way to come up with an analytical solution to that. Just you couldn't begin to do it. And it seems to work pretty well. But because I'm doing that a lot, that's one of the reasons why I am quite concerned about the efficiency. And I would love to have a version of APL that used more than one core. That would be great. Okay, thanks very much.